Welcome to this lesson on the swarm intelligence paradox in nanomotors. Today we're going to explore one of the most fascinating phenomena in nanotechnology, how individually weak nanomotors can achieve remarkable collective behaviors that seem impossible from a single motor's physics. First, let's understand what a nanomotor is. A nanomotor is a molecular machine that converts energy into mechanical motion at the nanoscale, typically ranging from 1 to 1,000 nanometers in size. A single nanomotor can propel itself at speeds around 10 micrometers per second, powered by chemical reactions. But when many nanomotors work together in a swarm, something remarkable happens. Here's the paradox. Individually, each nanomotor exerts a tiny force, typically on the order of piconewtons. Yet when swarming, they can liquefy gel barriers, pump cargo through confined spaces, and enhance diffusion by orders of magnitude. How is this possible? Each individual motor generates a force between 1 and 10 piconewtons. That's 1/1,000,000th of a newton, incredibly weak. The force from a single motor is approximately 1 to 10 piconewtons, which equals 10 to the negative 12 newtons. But when you have thousands or millions of these motors working together, they create collective behaviors that cannot be predicted by simply scaling up a single motor's physics. Let's start by understanding the physics governing a single nanomotor. At the nanoscale, the dominant forces are very different from our everyday experience. The key parameter is the Reynolds number, which measures the ratio of inertial forces to viscous forces. At the nanoscale, the Reynolds number is extremely small. The Reynolds number equals rho times L divided by mu, where rho is density, v is velocity, L is characteristic length, and mu is dynamic viscosity. For a typical nanomotor, the Reynolds number is approximately 10 to the negative 5. This means viscous forces completely dominate over inertia. At such low Reynolds numbers, if you stop propelling, the nanomotor stops moving instantly. There's no coasting or momentum like we experience in our macroscopic world. You might ask, if viscosity is so dominant, why don't nanomotors just get stuck and stop moving altogether? The answer is that nanomotors continuously convert chemical energy into mechanical work. They use fuel molecules like hydrogen peroxide to generate constant propulsion that overcomes the viscous drag. At steady state, the propulsion force equals the drag force, which is 6 pi mu rv, known as Stokes drag for a sphere of radius r. This gives us the velocity. V equals F propulsion divided by 6 pi mu r. For a 5 piconewton force and a 500 nanometer radius motor in water, velocity is about 10 micrometers per second. Now let's explore what happens when many nanomotors come together. This is where the swarm intelligence paradox becomes apparent. The first remarkable phenomenon is barrier liquefaction. A single nanomotor cannot penetrate a gel or viscous barrier, but a swarm of nanomotors can effectively liquefy the barrier. A single motor cannot push through the gel barrier, but when many motors swarm around the barrier, they collectively reduce the effective viscosity and can penetrate through. The mechanism involves local accumulation of shear stresses. Each motor contributes a small perturbation, but collectively they create regions of high shear that temporarily disrupt the gel structure. The total stress is the sum of individual stresses from n motors. When this exceeds the yield stress of the gel, liquefaction occurs. When total stress exceeds yield stress, the barrier liquefies. For a typical hydrogel with yield stress of 10 pascals, you need approximately 10,000 motors per cubic micrometer. This gives us a critical concentration threshold. Below this, no penetration occurs. Above it, collective liquefaction enables swarm penetration. The second phenomenon is enhanced cargo transport. Nanomotor swarms can pump cargo through microchannels much more efficiently than passive diffusion. You might wonder, how much faster is this active transport compared to passive diffusion? Let's calculate. For passive diffusion, the time to travel a distance L scales with L squared over the diffusion coefficient. The diffusion time is approximately L squared divided by d, where d is the diffusion coefficient. For a typical cargo particle of 1 micrometer radius, the diffusion coefficient is about 10 to the negative 12 meters squared per second, using the Einstein relation. To diffuse 100 micrometers, it takes approximately 10,000 seconds, or about 3 hours. Now, with a nanomotor swarm actively pushing the cargo at 10 micrometers per second, the time is just 10 seconds. a 1,000-fold improvement. The active transport time is L divided by swarm velocity, giving us 10 seconds. This is 3 orders of magnitude faster. The third phenomenon is diffusion enhancement. Even for particles not directly attached to motors, nearby swarms enhance their diffusion coefficient dramatically. The mechanism is hydrodynamic. Swimming nanomotors create flow fields that stir the surrounding fluid, enhancing mixing and effective diffusion of other particles. The effective diffusion coefficient equals the passive diffusion d0 plus an active contribution from the motor-induced flows. The active diffusion scales as phi versus squared tau, where phi is the motor volume fraction, v is motor velocity, and tau is the correlation time of motor motion. For 1% volume fraction of motors moving at 10 micrometers per second with 1 second correlation time, the active diffusion is about 10 to the negative 12, potentially doubling the total diffusion. Experimental studies have reported diffusion enhancements ranging from 10-fold to 100-fold, depending on motor concentration and activity. The swarm intelligence paradox is often compared to a phase transition in statistical physics. Let me explain this powerful analogy. Below a critical concentration, motors behave essentially independently. Their effects don't add up coherently. It's like water molecules below freezing, moving randomly. Above the critical concentration, collective modes emerge. Motors coordinate their motion through hydrodynamic coupling, creating large-scale flows and organized structures, like ice crystallizing from water. On the left, dilute motors move independently with no organization. On the right, dense swarms exhibit collective flows and coordinated motion patterns. The critical volume fraction is typically around 1%. Below this, no collective effects. Above this, swarm intelligence emerges. The theoretical framework for understanding these phenomena comes from active matter physics, a rapidly growing field at the intersection of biology, physics, and engineering. Active matter refers to systems composed of self-propelled units that convert stored or ambient energy into systematic movement. The basic equation is a continuity equation for density ρ. It includes diffusion d, nabla squared ρ, and an active flux term with self-propulsion velocity versus 0. This seemingly simple equation captures complex behaviors, density-driven instabilities, pattern formation, and collective migration not present in equilibrium systems. The key difference from equilibrium systems is continuous energy injection. This breaks detailed balance and time reversal symmetry, allowing for phenomena impossible in thermal equilibrium. An important question: how much energy do these nanomotor swarms consume to achieve their remarkable functions? We can estimate the energy dissipation rate. Each motor dissipates power equal to force times velocity. For 5 piconewton force and 10 micrometer per second velocity, power per motor is 5 times 10 to the negative 17 watts. For a swarm of n motors, total power is n times power per motor. For 1 million motors, total power is 50 picowatts. This might seem small, but it's concentrated in a tiny volume, creating high local energy densities. The swarm intelligence paradox in nanomotors has exciting practical applications emerging in medicine, environmental science, and nanotechnology. First, targeted drug delivery. Nanomotor swarms can navigate through biological fluids, penetrate tumor tissues, and deliver therapeutic cargo directly to cancer cells. Second, microsurgery. Swarms can mechanically disrupt diseased tissue or clear blocked vessels through their collective liquefaction ability. Third, environmental cleanup. Motor swarms can actively collect and transport pollutants or microplastics from water much faster than passive filtration. Fourth, lab-on-a-chip devices. Swarms provide active mixing in microfluidic channels, accelerating biochemical reactions and improving sensor response times. Despite the exciting potential, several challenges remain in harnessing nanomotor swarms for practical applications. First, control. How do we direct swarms to specific targets? Current approaches use magnetic fields, chemical gradients, or light to guide collective motion. Second, biocompatibility. Many nanomotors require toxic fuels like hydrogen peroxide. Developing motors that run on biocompatible fuels like glucose or oxygen is crucial. Third, stability. Nanomotors degrade over time. Typical lifetimes are minutes to hours. For medical applications, we need motors that function for days or can self-repair. Fourth, Manufacturing. Current synthesis methods produce motors in small batches. Scaling up to billions of motors with consistent properties is a major challenge. Let me show you a simple mathematical model that captures some aspects of swarm coordination, known as the Vicsek model. In the Vicsek model, each motor's velocity at the next time step equals the average direction of its neighbors multiplied by the speed versus zero. The average direction is computed over all motors J with an interaction radius, then normalized to unit vector. Remarkably, this simple local alignment rule produces large-scale flocking behavior, similar to bird flocks or fish schools, purely from local interactions. For nanomotors, alignment doesn't require explicit rules. It emerges naturally from hydrodynamic interactions between swimming motors. The swarm intelligence paradox in nanomotors mirrors behaviors we see in biological systems, from bacteria to animal groups. Bacterial swarms like E. coli exhibit similar collective behaviors: enhanced spreading, barrier penetration, and coordinated migration. Sperm cells swimming through the female reproductive tract show collective hydrodynamic interactions that enhance navigation efficiency. Even at larger scales, ant colonies demonstrate the same paradox. Individual ants are simple and weak, but colonies solve complex problems through swarm intelligence. These parallels suggest universal principles of collective behavior that span many orders of magnitude in size, from nanometers to meters. To rigorously quantify when collective behavior emerges, physicists use order parameters borrowed from phase transition theory. The polar order parameter phi equals 1 over n times the magnitude of the sum of all velocity vectors. It measures alignment. When phi equals 0, motors move randomly with no net direction. When phi equals 1, all motors move together in perfect alignment. At the critical density, the order parameter jumps discontinuously from near zero to finite value, like a first-order phase transition. This graph shows the order parameter versus motor density. Below critical density, order is near zero. Above it, order jumps to a finite value, indicating collective motion. We can also think about the swarm intelligence paradox from an energy landscape perspective, which provides deep insight into the stability of collective states. For individual motors, the configuration space is high-dimensional and rugged. Each motor explores its local environment independently. But for the swarm as a whole, collective coordinates emerge that define a coarse-grained energy landscape with distinct basins corresponding to different collective states. A simplified energy functional for the swarm is E swarm equals negative J times the sum over neighboring pairs of dot products of velocity vectors. This is analogous to ferromagnetic spin models in statistical mechanics, where spins prefer to align with neighbors, leading to spontaneous magnetization below critical temperature. Let me conclude with some exciting future directions and open questions in this rapidly evolving field. First, can we design swarms with programmable collective behaviors? Imagine swarms that self-assemble into specific shapes or perform sequential tasks autonomously. Second, what are the fundamental limits? Is there a maximum enhancement factor for diffusion or transport? What constrains collective efficiency? Third, can artificial nanomotor swarms learn and adapt to their environment like biological systems? This would require feedback mechanisms and memory. Fourth, most studies focus on simple 2D or confined geometries. Real biological tissues are complex 3D networks. How do swarms navigate these? Let me summarize the key concepts we've covered about the swarm intelligence paradox in nanomotors. Individual nanomotors are incredibly weak, generating only piconewton scale forces, and operating in the low Reynolds number regime where viscosity dominates. Yet collective swarms exhibit remarkable emergent phenomena: barrier liquefaction, active cargo pumping, and orders of magnitude diffusion enhancement. The transition from independent to collective behavior resembles a phase transition, with a critical concentration separating the two regimes. Active matter physics provides the theoretical framework, treating motors as self-propelled particles that break detailed balance through continuous energy injection. Potential applications span targeted drug delivery, microsurgery, environmental remediation, and lab-on-a-chip technologies. Finally, let me emphasize the core insight of the swarm intelligence paradox, the principle of non-scalability. You fundamentally cannot predict swarm behavior by simply multiplying single motor properties by the number of motors. Qualitatively new physics emerges. The effective force of a swarm does not equal N times the single motor force. Collective modes, hydrodynamic coupling, and self-organization create capabilities beyond linear scaling. This is the essence of emergence in complex systems. The whole is fundamentally different from the sum of its parts. New properties arise from interactions that are not present in isolated components. Understanding the principles of emergence enables rational design of nanomotor swarms with desired collective functions, rather than relying on trial and error. The swarm intelligence paradox in nanomotors teaches us a profound lesson that extends far beyond nanotechnology. It shows us that individual weakness is not an insurmountable barrier to collective power when proper coordination and cooperation emerge from simple local interactions. Nature discovered this principle billions of years ago, using it in bacterial colonies, cellular tissues, and ecosystems. Now we're learning to harness it technologically. Perhaps the future of nanotechnology lies not in building ever more sophisticated individual machines, but in orchestrating vast swarms of simple components that exhibit collective intelligence.